Okay. So what is the plan? You begin, I sure that
well, wait 1 minute to see, to get the maximum number of faculty members. I see only Dr. Qais, yourself.
Okay.
Maybe we can send them a reminder again. I don't know.
Yeah, maybe this is the problem of they don't have the habitude to go through Zoom, maybe, and people maybe miss the link.
Well, the link is very simple. Just open it, it will pop up.
Yeah, sure.
I'm sending a reminder right now.
Let's see the number of participants. Dr. Yes, I think
Dr. Hisham.
You can begin at least to introduce maybe the center or yourself, whatever you want. If you want I to introduce you or you want to introduce yourself, whatever you want, I will do for you.
Okay, you can introduce me and then we'll start, inshallah. Go ahead, Dr. Hisham.
Yeah, okay. Dr. Elias is an astrophysicist, right? And
yes.
he is working as a director of SAASST, and is also associate professor at the Department of Applied Physics and Astronomy. And since I am new here, but I know him, and I am impressed the way that the SAASST has developed within few years due to the hard work of Dr. Elias. And I am happy to mention this and to introduce him. I think I don't have a lot of information more than that, but I am impressed of the work of Dr. Elias, and I invite the people to hear about all his group of research. Thank you, Dr. Elias. You can begin.
Thank you very much, Dr. Hisham. I appreciate that. So thank you very much. So thank you for all the faculty members and for all the research assistants to attend today's seminar. So in this seminar, I wanted to present what our research assistants are doing as a research, especially for the coming IAC 2020 CyberSpace edition. We had 8 papers accepted, and hopefully we're going to present them today one by one. So as we come to the research assistant, I will present him, and I will let him or let her present his own work. So here are the papers that have been accepted. So as I say, we have 8 of them, ranging from radio astronomy to CubeSat to high energy astrophysics. And also to planetary science. So hopefully, these papers will give you a good background about what we are doing at the academy. So let me start. So the first one is myself. I have 2 papers here. I will be the first one and also the last one. So this paper, the first one is about building an artificial Martian atmosphere and how long it will stay hovering As you know, Mars has a very thin atmosphere, even though 96% of it is carbon dioxide, but it is so thin that if you were to land there without any proper protection, you're going to fall like a dry stick. There is not enough pressure to keep your water running or your blood running. So this paper is about how can we build an artificial Mars atmosphere and how much time can it stay over there. Knowing that Mars has a very weak magnetic field, it is not like Earth, it has a magnetosphere and so on. So this paper is with my son Ridwan, Arzu, Maytha Shamsi, and also Mariam Al-Qasimi. So most of this were students, and now they are, some of them are working with us. So this paper has 6 sections, but it took only about 2 or 3 just to be short, because each one of us will have only 5 minutes to present his or her work. So to introduce the problem, first of all, that this research is in line with the recent Emirates Mars mission that will arrive hopefully end February, early March, and hopefully by May we're going to get a lot of data from it. So it's like is to prepare us how to handle that data, how to understand the Martian atmosphere. So the Martian atmosphere is very thin, as I said. Most of it has escaped. It is said that 3.5, maybe 4 billion years ago, it was a live planet. And what happened to it? Maybe it is because of the sun, because the Mars lacks a magnetosphere. So the sun was able, or the solar wind, these highly charged particles were able to strip all of this Martian atmosphere. So I would like to do what? We'd like to simulate the buildup of an artificial magnetosphere by injecting or inducing gas into it. We're going to do it in 2 different ways. We're going to inject a neutral atmosphere, and also we're going to inject an ionized atmosphere in order to take into account the solar wind. So in the first model, artificial neutral atmosphere, the impulsive case, meaning that we're going to inject particles is like what a rocket does, to inject gases for a fraction of a second. So we're going to start with a maximum distribution, making some assumption. Most of the assumption here is built upon gravity. We're going to assume it to be constant within a box no bigger than 200 kilometers. So because we're going to do an analytical work, we're going to derive some equations, and to do the work right, to have an easy analytical derivation. So we're going to assume the Martian gravity to be constant within this box. Then we are able to compute the total density. It all depends upon what? It depends upon the mass particle and also the surface temperature. So this plot to the right, we're going to see what? We see the density as a function of time. And as you can see, the density is going to increase. This is for oxygen, T equal to 350. By the way, the Martian temperature are between 200 to about 350. So 200 is 9 times 350 is daylight. So it is very cold there. As you can see, the atmosphere is going to build up, yes, but it's going to go down very quickly. So there is in each of these 4 plots, because we're doing it at different location from the injection point. This is for R equal to 0, R equal to 10 kilometers, 50, and also 100 kilometers. So in all of these curves, so there's a buildup of an atmosphere, but at some point it will decrease. So the inflection point is here is very important to tell you how long that atmosphere will stay. So it will stay for a couple of months only. Doing the artificial ionized atmosphere. So this is a continuous case. We're going to continuously inject particles. What kind of continuous case we may have in the future if you have, let's say, a Martian base, or maybe you do mining. So we're going to inject the gas all the time. In this case, we're going to take into account the sun electric field. So that we're going to have in one equation the electric field, and we're going to obtain a very different complex equations. And again here, the build-up of the atmosphere, yes, it's going to go up to some limit, but it's going to decrease very sharp. In this case, for the continuous case, for the ionized atmosphere, the atmosphere doesn't stay a lot, maybe just a couple of hours to a couple of days, in comparison to the neutral atmosphere, where it can stay for a couple of months. So this work has been to simulate the build-up of this Martian atmosphere, how we can more or less, if we can in the future, terraforming, meaning that transforming the Martian atmosphere to a livable atmosphere. So for the neutral atmosphere, the growth of the atmosphere is steady. After about a couple of months, then it will escape to space. For the ionized Martian atmosphere, by introducing the sun electric field, these symmetric gases or this artificial atmosphere, these stay only for a couple of hours. Maximum it was about maybe 5 or 6 days. So it means what? It means that the sun, solar wind did play and is playing and will play a very effective role in terms of stripping the Martian atmosphere. And this was also what has been observed by the US MAVEN spacecraft, where it was able to observe that some part of the Martian atmosphere are letting gases escaping. Why? Because the sun solar wind is pushing these charged particles away from Mars. So this is the work that we have been doing in this paper that we presented next week in the coming IAC 2020 CyberSpace edition. I will leave the question at the end if possible, Dr. Hisham. Okay. So the next paper will be by Ms. Asma Al-Hamid. She is a research assistant at the Radio Astronomy Laboratory, and she'll be talking about the new 40-meter radio interferometer. Okay, Asma?
Yes, Assalamu alaikum, Doctor.
Salam. Let me know when I move to the next slide, okay?
Okay, all right. The paper that we have participated with in the IAC 2020 is observing at 1.4 gigahertz with the Chardonnay 40-meter radio interferometer. And this presentation is to give you an idea on what is this new system. These are my co-authors in the same paper. So now we go to an introduction on the system. Yes. So this is a first of its kind system in the Middle East or the North African region. The system works on 1.4 gigahertz, or in the wavelength, it's 21 centimeter, which is the frequency for the hydrogen line emission. The system is basically a 5-meter radio telescopes. Each one of them is 5 meters in diameter, and they're all from the Italian company Primaluce Lab. And the type of the system or the telescope is Spider 500A. So the 3 telescopes together form a scalene triangle, and the distances between them, or the sides of the triangle, is 30, 40, and 50 meters. So the 40-meter interferometer has an angular resolution of about 0.3 degrees. Okay, and a collecting area of an antenna 8.7 meters in diameter. So now we go to one of the results that we have obtained using one of the telescopes. So this is a radio map of the sun taken on 5th of January in 2020, and it is a map created by one of the 3 telescopes, not the interferometer. So one of the resolution is about 3 degrees. So the observation program that we have, or the projects that we are going through in the lab, is we have many of them. Some of them are ongoing, some of them are for future work, like studying the structure of the Milky Way or the rotation curve of the, to determine the velocity of the hydrogen clouds in the spiral arms, and to observe hundreds of extended radio galaxies. We have a list of 72 sources, radio sources, that we can use to study. We can study them, using this system. And of course, to calculate the masses of galaxies and study the dynamics of individual galaxies. We have plans to search for extraterrestrial intelligence and to perform extensive radio surveys of different objects of the solar systems. We have current projects now on this point. And at the end, we plan to establish an educational observatory to teach radio astronomy and as a research tool for the new radio astronomers. So right now, if you go to the conclusion, yes, thank you. So we are now in the last phase of the system, which is just to have to connect the interferometer correlator. This way we can get the 0.3 resolution, and at the same time we have to upgrade the cables to RF cables we have to upgrade the RF cables to fiber optics to minimize the loss of signal. And at the end, the plan to extend the project is to have 6 more antennas and to have a very large extended array with a baseline of 400 kilometers. Thank you.
Thank you very much, Asma. We go next to the CubeSat laboratory with Mr. Ibrahim Sebt. Mr. Ibrahim Sebt has a BSc in aerospace engineering, and he come from Khalifa University, and he will be presenting CyberSat-1 thermal analysis for orbital launch selection. Please, Mr. Ibrahim.
Thank you, Doctor. So I'll be presenting, as Dr. Yas said, CyberSat-1 thermal analysis for orbital launch selection. Next slide, please, Doctor. So in terms of the thermal design of CyberSat-1 consists of 2 models: the geometrical model, which describes the geometry and the nodes and the meshing of the satellite, as well as the thermal model, which describes the mathematical representation of the capacitance, conductive couplings, and the heat dissipation profiles of the subsystems. So in order to prepare these models, we've used ANSYS, a space claim, which is a tool for cleanup of the geometry. And we have also simulated we have run the whole simulation through Systema Thermica software, which is used to mesh and set up the trajectory and kinematics adjustment interface. Also, the simulation was performed on 2 different orbits, 5 kilometers altitude, sun-synchronous, local time descending node, and local time ascending node at 10:30. So in terms of the mesh of the thermal design, it is mostly square plates, since the satellite is made up of PCB boards. And also, it is important to mention that the thermal design has details about the materials used in the satellite. Next slide, please, Doctor. All right. So in terms of the power consumption and the runtime of the subsystem, it was set to simulate real-life scenarios. So in terms of the bus system, the UHF-VHF modem will run in the 1st, 3rd, and 5th orbit for 20 minutes, and in the middle of each respective orbit. However, for the S-band, it will run for 10 minutes in the 2nd and the 4th orbit. And the ADCS consists of different units, thus each unit will run at different intervals. So for example, the GPS will run for 10 minutes in each orbit. The magnetic torquers and their action wheels will run for 30 minutes, for 30 seconds, and will stop for another 30 seconds, while the star tracker will work for 5 minutes and stop for a minute for the entire simulation time. Also, the EPS, the batteries, and the OBC will be running continuously. However, in terms of the payload, the IXRD, which is the improved X-ray detector, will run for in the 2nd and the 4th orbit. But before that, the satellite will reorient to the correct attitude. Next slide, please, Doctor. So, in terms of results, these simulations the results of these simulations are represented in table 1 and 2, which shows the maximum and minimum operational and calculated temperatures, which are illustrated further in figure 2 and 3, and it illustrates that both orbit temperature ranges fall within the acceptable ranges. So we can conclude by saying that, next slide, Doctor. So we can conclude that the calculated temperatures differ between the 1st and the 2nd orbit, but however, they both fall within the acceptable ranges. The 1st orbit temperature is slightly lower than the 2nd orbit temperatures, but that can be explained due to the different exposure of the satellite panel to the sun when it is in the local time descending node or the ascending node. Thank you.
Thank you very much, Ibrahim. Next is Tarifa Al-Kaabi. She is also part of the research CubeSat laboratory. So she will talk about the ground station and how it can be used to track and also control our SAASST satellite. Please, Tarifa.
Thank you, Dr. Elias. So, as you said, I will talk about the SAASST ground station for satellite tracking and control for high data rates. Next slide, please. So, as we know, ground stations are important because they give us the necessary communication interface with the spacecraft. And here at SAASST, we have completed the installation work of a UHF-VHF ground station in February of 2020. That was in preparation for the launch of our first CubeSat of the Academy, ShajaSat-1. It also serves to set up the infrastructure for future satellite missions, inshallah, and as an educational tool. So our 3U CubeSat mission, ShajaSat-1, has the main payload of an X-ray detector to investigate hard X-ray emissions from the sun and other bright X-ray sources in the universe. And the data of the payload would be transmitted with an S-band transmitter, while the telemetry and commands would be communicated over with the VHF, UHF antenna, the transceiver. And so our ground station should support communication with our CubeSat in the mentioned frequency bands. Next, please. As for the setup, you can see here the hardware and software that we have implemented. The hardware can be classified as outdoor and indoor. The outdoor includes 2 UHF antennas and 2 VHF antennas, both of the Yagi type, and the rotator that gives a turning range of 180 degrees in the elevation and 360 in the azimuth direction. The cables and the mast that holds everything in place. While the indoor consists of the ICOM 9700 radio transceiver, the elevation and azimuth dual controller, the rotator control interface, and the ground station computer. And these hardware implemented give us the possibility of controlling the full autonomous control of the system, and also from inside of our CubeSat lab. As for the software, the ham radio deluxe can be used to track and listen for amateur satellite signals with the 3 modules that we have here: the rig control, the satellite tracking, and the rotator control. And additionally, we have a custom-made ground station console software that we have designed to provide mission control attributes for our mission ShajaSat-1. And it provides the users with the means to interact with the CubeSat in orbit with the 3 main functions. The first would be to issue telecommands, and all telecommands are available as buttons, as you can see here. And the second would be to process and display telemetry, and this includes general telemetry packages and telemetry of the individual subsystems. And the third would be to export telemetry and photos to be saved on the hard drive. Next slide, please. So finally, the ground station plays a big role in capacity building and student education here at SAASST. It is currently being used by students and researchers for training purposes. And the team is officially licensed to operate it after undergoing intense training sessions organized by the Emirates Amateur Radio Society. And at the moment, the ground station is fully operational in the VHF-UHF amateur frequency ranges and has been successfully tested with different satellites. And inshallah, S-band capability would be added in the future to support the download of the ShajaSat-1 payload data. Thank you.
Thank you very much, Tarifa. We go next to Antonios, Dr. Antonios, a newly faculty member of the Applied Physics Department and also part of the SAASST research team. He is responsible for the high energy astrophysics research lab here at SAASST. So please, Dr. Antonios.
Hello, I hope you can hear me.
Yes, we can.
Yes. So the title is how do we see the high energy astrophysics group here at SAASST in the light of ShajaSat-1 and other future projects. You have already seen the list of authors on the previous slides, but that's fine. I hope you know me, as I have been here for a few years. So we can go to the next slide. So not to spend an extended introduction. One of the major tasks, one of the major research studies is X-ray binaries. And what is X-ray binaries? As the word says, is a binary system that it is bright in X-rays. It's as simple as that. Then if you want to start playing with the different sources and do a bit of taxonomy of these sources, you will realize that there are different categories. And you can classify them based on their compact objects or the donor star or many, many different objects. The most common category that we are having here is according to the compact object. If the donor star. If the donor star is a massive star, a few tenths of the mass of the sun, then we call this system high mass X-ray binary. And in these cases, in this high mass X-ray binary, most of the accretion is occurred via direct stellar wind accretion, or in some very extreme limiting cases, you might have transient disk accretion that seems a bit more complicated. On the other hand, if your star is roughly a few times or around the mass of the sun or even lower, then you have what is known a low mass X-ray binary. In the low mass X-ray binaries, these systems are not as powerful as their cousins, their high mass X-ray binaries. So accretion will not directly occur as we have seen in high mass X-ray binaries. They will form a steady accretion. Disk accretion will start slowly, and these sources can become quite powerful in X-rays. Different phenomenology, different accretion processes, but both of them, they share one common characteristic. Both of them are very, very bright in X-rays, and we can study. Of course, in our laboratory, we have more projects than that we are discuss later, like simulations of matter very, very close to a black hole, accretion onto a neutron star, that the magnetic field starts to play a dominant role. But for the general picture that we would like to discuss here, the good representation that we need to have is how X-rays are produced, either via direct wind accretion in high mass X-ray binaries or via an accretion disk in low mass X-ray binaries. And this one comes into the next slide, that I'm presenting again something that you have seen it, but from a different perspective can we go to the next slide, please? On our SAASST. What is our SAASST? I mean, you have seen the thermal analysis, you have seen how we communicated with the ground, but why we did all these things? I mean, obviously we did all these things to learn how to construct a satellite, but learning is not enough. You need to utilize it. For this satellite, for future satellite, you have to utilize it somewhere. So first of all, and I don't want to minimize the importance, first of all, we need to know how to build things. Second of all, we need to have a nice case to study. And in this case, in collaboration with Sabancı University in Istanbul and Istanbul Technical University, on this SAASST1, we will employ an improved X-ray detector. Why we call it improved? Because there was a previous version on a previous satellite that it was not very successful. So here we have an improved version of this detector called IXRD. What is IXRD? It is a detector to study X-rays in the space. The technology of this detector is based on cadmium, zinc, tellurium crystal, that this crystal is capable to absorb X-ray photons and record a signal in the energy range 20 to 200 keV. So this one is rather hard X-rays. Imagine that the chest X-ray that we get is around 10, let's say 20 maximum keV energy range. So these X-rays are much, much harder than what we should expect from a chest X-rays. So why we need to study things at that extreme energy? Because at that extreme energy is where these X-ray binaries are signing. And we need to have a sensitive detector in space. As you know, these wavelengths are absorbed in the atmosphere. We need to have a reasonably good spectral resolution at around 60 keV to study the broadband emission of these sources, because depending if you have wind, if you have disk, if the disk is large one or if the disk is small one, the shape will change. So we need to have the spectral resolution to record this space, and this instrument will be actually ideal for observing bright galactic X-ray sources like Cygnus X1, which is one of the brightest galactic X-ray source, which is a high mass X-ray binary hosting a black hole of around 10 solar masses. In addition to that, because these detectors are rather wide in the field of view, so they can see quite large part of the sky at the same time, it will make it ideal to study transient phenomena that they are coming like a burst and then they disappear. What can these be? Gamma ray burst, and most importantly, if we have any electromagnetic counterpart to these gravitational waves that are becoming very, very popular these days. And actually, there are proposals in order to make constellations of CubeSats, slightly larger than ours, but not much larger, in order to study these events. Because why? CubeSats are rather cheap to construct with respect to a larger satellite that you can cost you a few billion dollars. Second, if you have it in a constellation with triangulations, you can pinpoint where this transient event it is, and you can correlate it with triangulation that you use on gravitational waves on the Earth. And then you can say to the optical astronomers that their field of view is much, much narrower. Look, go and see there, something is happening. And at the end, I will come with my conclusion, where we stand, where we are. First of all, computational simulations and observations are needed to work together to shed light on accretion physics. This one is of paramount importance here, especially in the light of the upcoming master in astronomy and space science, because this will offer a hands-on opportunity for the students to work on a currently developed SAASST, and they have already gathered experience for data analysis in X-rays. Studying accretion at extreme environments is of paramount importance, either if it is a black hole or a neutron star. As I have already mentioned, SAASST-1 will be a great asset in studying galactic X-ray sources, either persistent or transient. But not only that, we should see beyond that, we should see that this is a tremendous instrument also for students to learn. And last but not least, that I keep put in most of my slides, we need future realistic simulations. And if you wish to translate it in words that everyone can understand, future, it means you have to work. Realistic, it means you have to include more physics. And simulation, it means that you should introduce a lot of CPU time. Luckily, we have a rather small cluster at the university. Hopefully, we should expand and host more clusters either at the university or at SAASST here, not only for simulations, but also for data analysis, data mining, artificial intelligence, and all these things that are quite important these days. And at that point, I will stop. Thank you very much for your time. I already consumed more than 5 minutes. And thank you.
Thank you very much, Dr. Antonio. So we move to Mr. Mohammed Talafha. He's going to talk about the Sharjah Lunar Impact Observatory lunar flashes. Please, Mohammed.
Thank you, Doctor. Thank you, Dr. Yes. The first slide was about the authors, me and Dr. Ilyas, Dr. Hamid, and we have two students. they were with us when we discovered the first impact. Behind me here in the virtual, this is the our telescope, a small unit, 14-inch here, just close to the radio telescope. What's the lunar flashes? Lunar flashes, we know always Moon and Earth is same unit or same target. If anything happened in Earth, it's happened on the Moon. We here focus on these space rocks. It's sometimes sporadic, sometimes coming from this meteor shower. Every day there's 30,000 kilograms of meteoroid hits the Earth every day. Most of them, maybe 99% of these 30,000 kilograms, it's burning in the atmosphere. But the different or the big difference between Earth and Moon, there's no atmosphere around the Moon. This is give us a good opportunity to see this impact, because these small rocks can reach to the surface and hit the surface in same supersonic velocity. This velocity gives a small particle very high energy, kinetic energy. For example, just the last point here, the fourth point, just if we have 5 kilograms of this space rocks with the average velocity 35 kilometers per second, will create a 9-meter crater on the Moon surface. It's very high amount of energy, kinetic energy. We're looking for, and in fact, in physics, we're looking for very small fraction of this kinetic energy generate invisible light. It's coming in invisible light. It's almost 5 to the 10 to the power minus 4 of total energy we can recognize here on Earth. Please, next. This is the how to observe flashes. This is just all this diagram. It's a hardware. For example, for sure, we need a telescope and a camera. The special camera needed to be a little bit sensitive in IR. And GPS for timing, convert with from analog to digital video, and monitor computer hardware. And after this all this hardware is the first step of observation. There is number one, there is number 0 or 0 step, and 1, 2. The next one is the hard software, how to analyze and confirm and know exactly this space rocks, how much it's long weight or velocity, which meteor shower belong. Everything you need to understand more about this space rock if you found a flash. Next, please. We just start since 6 months ago. And this time we, after almost 4 days of observation, we found the first impact. This impact, we need to confirm this impact. We found another telescope in Greece. Most of these researchers, Dr. Antonis' friend, I'm sent him. I found something here, impact of flash, small flash. They check the archive and they confirm we observe same impact in same time. And because this telescope is belong to ESA, they make publish something in web story in ESA, and we as a science we confirm this impact, and they are the first time they impact by other telescope. This is very important. Now, after 6 months, we have more than this. We have another impact, and we have other 2 candidates. The total, we have 4 impacts until now. That's all, and we observe every month 4 to 5 days every month after sunset. Thank you, Doctor.
Thank you, Talabha. And we go to Mr. Rayhan, Mohammed Rayhan. So he's part of the radio astronomy lab. He's going to talk about another radio system, a decametric radio system that works at 20.1 megahertz. Rayhan, please.
Assalamu alaikum, Doctor. Good afternoon, everyone. I'm Mohammed Rayhan, research assistant from Radio Astronomy Lab in SAASST. I'm here today to summarize the decametric radio telescope scientific paper as a contribution in IAC 2020. Our paper's title is Detection of Jovian Radio Emission at 20.1 megahertz with a decametric radio array installed in SAASST. The project in brief, next, yeah, I think the previous one, Doctor, please, the purpose. Okay, yeah. This project in brief, this project is funded by UAE Space Agency to conduct radio astronomy for a wide sector of students from high school to PS by observing astronomical events as a radio emission from the planet Jupiter and the Sun. Also, advanced research could be done. For example, a different pattern of these radio bursts might be affected by different factors, like the ionospheric status. That means there is a wide area of research is offered in this field. Next. As a result of our observations, let's talk about the Jovian radio storm on April 26th, 2020, when the decametric dual array detected the most obvious and typical Jovian S burst we ever get. Although the angle between the Sun and Jupiter was greater than 94 degrees, this burst was classified as an IOA type, and it lasts for 25 minutes. On the left, we can see the tendency of the received signal, and the individual spikes represent the short type of Jovian radiation. The chart on the right obtains the prediction of Jupiter and Jupiter IO system radio emission on the chart, and we can use the Jupiter Pro software to predict this kind of events. Next, please. Yeah. In terms of solar observations in the same year, 2020, the graph on the left represents a very short solar emission observed as a decametric radio burst on May 20, 2020, but no sunspots were associated with this emission. On the right side, there is another solar radio burst that happened on January 11th, 2020, and the sunspot number 2765 or 2765, that was classified as a member of the new cycle, the 25th solar cycle. It was associated with that burst. Both bursts are a good example of the shark fin-shaped graph that characterize the typical solar radio emission. Finally, the conclusion, during the period from July 2019 to May 2020, the DRT arrays in SAASST detected 7 different Jovian radio emission events. Moreover, during the period from January 2020 to May 2020, it detected 4 different solar bursts. Besides, the study proved the relationship between the sun's seasonal declination and the ability to receive the Jovian radio storms. More observations would obtain the solar activity effect on the intensity of the received Jovian decametric radio emission. So it will be, inshallah, it will be done in the upcoming year. Thank you for listening.
Thank you very much, Mr. Raihan. And this will come up to the last talk here, promoting STEM through the Sharjah Academy for Space Sciences and Technology. So this is a paper about how SAASST has been used to attract students to follow science, technology, engineering, and also mathematics. So just talk about what we have in terms of space sciences. So we have the Department of Applied Physics and Astronomy, about 25 faculty members, 6 of them are astronomers. Presently, which is quite good, it's one of the largest departments in the whole main award. 70 students, some of them are doing the applied physics degree, and some of them are following this petroleum geophysics program. We have 5 undergraduate courses, and because of the MSc in Astronomy and Space Sciences, we have now about 20 graduate astronomy courses. Sorry. In terms of staff, so we have a large number of research assistants. We have 16 of them, 8 space science laboratories, and also 3 observatories, 2 optical and 1 radio. In terms of research, I believe we are very well versed in space sciences, astronomy, remote sensing, artificial intelligence, I'm sorry, high energy astrophysics, and so on. And as all of you know, so we have this new MSc in Astronomy and Space Sciences, the MSc in Remote Sensing, and also this MSc in Air and Space Law, and hopefully by next year, this MSc in Aerospace Engineering. So all of these programs are very, very helpful because they will attract tens of students to the Department of Physics and also to the College of Engineering, because they would like to follow these programs that do have space applications. So how are we attracting students? Well, just to show you two histograms, these are the number of students that we have. We're able to accept at SAASST to do their internship. 2018-19, we have 13 students, and look at 2019-2020, it almost doubled. And as you can see, they come from all departments, electrical engineering, aerospace engineering, from Khalifa University, mathematics. Like this past academic year, this past summer, we had about 7 students from the math department from the University of Sharjah. Mechanical engineering and nuclear engineering, and also, so we have a lot of students coming to us. So we are attracting the student at least to check that studying science, studying technology, and also studying engineering and math is something that can be very useful into space sciences applications. We are also accepting international students. As you know, the University of Sharjah is part of this program IAC, which is exchange students. Up to now, so we were accepting students since 4 years ago. I recall the first student was from Japan, and now he's finishing his PhD in the US. And so every academic year, we receive students from everywhere. So as you can see, the number is quite steady. This year, 2020-21, we're supposed to receive at least 6 students, but because of the pandemic, so we decided not to do so, just for health reasons. So we do accept this international student to do that, because this student, they do request us to be here. So they see us on the internet, they see what we have as research labs, and they would like to come to us. So just to summarize, we have 8 established research labs, well established and working fine, 3 observatories, 6 scientific instruments, worldwide instruments, from CubeSat to space weather, to radio astronomy, to Sharjah Optical Observatory. We have up to now more than 42 publications in peer-reviewed journals. SAASST, in the past 3 or 4 years, has done more than 48 workshops, STK workshops, CubeSat workshops, teachers workshops. So all of these were done here at the Academy. We have presently 16 research assistants spread over all the research labs. The Department of Applied Physics and Astronomy has more than 70 students. This is a very good sign that students are being attracted to science. And also we are able to accept more than 50 internship students. And even this semester, we have a couple of them doing research with us. I believe I skipped one slide. I'm sorry. Or maybe, no, that's it. Okay, so this is it. And thank you very much for accepting us to be part of the Department of Applied Physics seminar series. So now, if you have any questions, so please feel free to ask.
So let me begin with the question. Do you hear me?
Yes, please.
Yeah. for the Sat1 Sharjah, when it will be launched?
Well, we are planning to have it launched in Q2 2021.
Excellent.
If everything goes well,
Yeah.
because we're having trouble reaching our Turkish partner to exchange component and so on. So, but it is planned to be Q2 2021.
So do you have a plan to add something, or already settled all the components?
Yes. We have a second one, a GNSS satellite, and Dr. Mubashir will be responsible for it. Well, the main vision of the CubeSat lab is not to be a one-shot CubeSat. So SharjahSat is just for a way for us to form our research assistant to have that know-how. So we are planning the second one, GNSS, and would like the CubeSat to be like a business CubeSat. So we would like to build a CubeSat for government offices and for government departments in the near future, inshallah.
Thanks. We are waiting for other question, right?
Yeah.
So since no one asked, I can ask more. So have you any more idea about some range of frequency to detect stars, binary stars or something? I mean, detectors that they are out of the range that you have. Are you planning to get more wide range of frequency of detection for stars and so on?
Well, we have the optical observatory. I believe, if Antonios can correct me, would like to participate in a space program that will mainly observe, I believe, in the infrared, detect not star, but to detect exoplanets. So hopefully we'll be part of the space program. So it is under study. We have our radio observatory, so we can observe galaxies, extragalactic objects, and so on. So we can observe in the radio band. Yes.
So do you have a planning to extend the SAASST for other laboratories? On which laboratory are planning to build on?
Yes, we have several labs. First of all, we would like to have a data center. We are planning to have this artificial intelligence lab. Also, a space robotic lab. This may be in 2 years' time. Also, we are planning to have here not a lab, but a machine shop to build our own tools. This is and hopefully, so we'll be getting 2 big machines in the near future, maybe by next year, thermal vacuum chamber and also barometric table for to test not only satellites but anything that the university may have as experiments, like for the College of Engineering and also the College of Sciences. So these 2 big machines, they cost a lot. They may reach 4 million dirhams. So we're going to get them with the University of Sharjah together. Yes,
so
we have
for the Mars mission, where the Hope mission, I think are you planning to get data to work with that and so on to build the lab?
Yes. So we have this in line, this planetary science lab or Mars lab, and hopefully once we get the right person into it, so we can promote this research. Yes, we are part of the Martian mission since more than 4 years. I believe Dr. Ata was with me when we were meeting with the Mohammed Barash Space Center, and hopefully they know that we do have a solid university and also solid research labs here that to promote us. Yes, Dr. Mashhour, please go ahead.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you for the nice presentations. Actually, I have two questions. Maybe one for concerning the radio telescope, the other concerning the X-ray telescope for Antonius. The first one is for the radio telescope. You mentioned that you have a resolution of 0.36. So when we are talking about such a resolution, and we keep in our mind that the sun is 0.5 seconds of arc, so you are just observing the whole disk of the sun. So what features can we focus with such a resolution? I mean, either for the sun or for Jupiter, or it would be maybe better to focus on other phenomena like something in the galaxies. You are a specialist in galaxies, or to focus on some clouds, to some gas clouds. So what's in your opinion? This is the first question. The second question also concerning the radio. Why we don't connect our radio telescope with a universal network? There are some networks that they are working together. It would be very powerful, and it will be something great to have it connected with such networks.
Yes, for your first question, so the single telescope has very low resolution. It is meant to observe very extended sources, extragalactic, above 1 degree. When the 3 telescope will start working as a real radio interferometer, we can resolve any extragalactic radio source. As Asma said, we made a table of 72 sources that we can observe easily with a 40 radio interferometer. So up to now, yes, the resolution is very low because it is long wavelength, a small dish. But in the near future, when the full 40 meter is working, it will have great resolution capabilities. So we can observe extended objects. We can observe, let's say, the clouds or the spiral arms of our Milky Way. We can map the 21 centimeter along the spiral arms of our Milky Way galaxy. We can do that for sure. With such a low resolution, you cannot see the details of the sun or Jupiter. So this is meant to observe extended objects. In terms of connecting our telescope to other network, yes, this is what we have in mind since the beginning. So hopefully when the 40 meter is installed, so we can have it as part of what you call the very long baseline interferometry. So we can associate ourselves with other network. We have also a plan, if we can, because we have to change the receiver, plan to use it in the next black hole observation of our Milky Way galaxy. So to have a greater and greater resolution with the baseline maybe more than 10,000 kilometers. Yes, we have a plan for that, yes.
Oh, that's great. So Antonius, Dr. Antonius, please. You talked about 6 keV resolution power, around 60 keV in the spectrum for the X-ray. So that would be okay for to observe Cygnus X1. By the way, I used such X-ray for this system with Professor Anami since maybe 20 years ago, and we published a paper on this star. But what we actually need a precise eclipsing light curve, either in the photometrical or in the visible, or in the X-ray. So we can observe it using the visible. We can use our Sharjah Optical Observatory to observe this source, say Cygnus X1 or any other bright source. So can you observe when you launch, I mean in the future, when you launch this satellite CubeSat, can you observe the whole period, to get the eclipse?
Yes, in theory, yes. I mean, depends on your planning of your observations. I mean, it will be limited because of the orbit, but yes, you can do it. You can select your time periods to target the source for long enough in order to to have resolved the orbit, and you can see the eclipses as well. Yes, you can do that.
That would be great to have both the optical light curve and to have the X-ray light curve. By this way, you can actually get all the fundamental parameters of the binary. And to
The
get
orbit
more
of the
information
binary,
about
yes.
the compact object, yeah.
But currently there are much better instruments for that. There are all sky monitors that you can get the light curve.
Yeah, I know we can
much
get it from
larger
other
time span.
telescopes. Yeah, but what's in my mind is to use our instruments, even with low resolution, even with not that big amount of data, but at least to publish something from our
yes,
SAASST,
but I mean, the all sky monitors, they are completely different in design because they have large field of view. In our case, we have to target our satellite there, and this one will reduce the available time and the exposure time significantly. On the other hand, and of course the coverage of the orbit. On the other hand, you have instruments like SwiftBat or the Japanese Maxi on ISS, or older instruments like All Sky Monitor on RXT, that you constantly observe the sky, and you can have tremendous amount of data. With SwiftBat, you can have roughly 12, maybe 13 years of data for the bright sources. For Cygnus X1, for Vela X1, for the very, very bright sources, you can have tremendous amount of data using All Sky Monitors. In our case, of course, we can do it, but because the effective area of the detector is much, much smaller, the quality will not be as good as you will see it on the All Sky Monitor, so you cannot see details on the ingress and the egress, and if there is any asymmetry there between ingress and egress. And the problem is that even with our satellite, because there will be a collimator and will narrow down significantly the field of view, still quite large with respect to optical astronomy, but quite narrowed down for all sky monitors, you will lose a lot of time based on orbital constraints. So yes, we can do that. We can study the light curve along the line of sight, but currently we have instruments that they are spanning more than 20, they have data spanning more than 15 years that you can do it in much, much better accuracy. Because
yeah, of course, but
you have,
we need 1 or 2 points just to add it to the let's say to the international data which is available on the net. Just to add a few points, these are my points from SAASST. We have this, we have this, we have this. 2 or 3 points from the light curve, that would be great.
Yes, this one can be do, but the idea is to have targeted observations because it's not designed to be an all sky monitor. You can put a couple of points, but will not improve much. One of the things that is all these small satellites are very capable of is besides the bright objects that you can do a bit of science, but not something tremendous. One other object of interest for CubeSats is transient events like gamma ray bursts, which is much, much easier to rotate a CubeSat to the particular direction rather than waiting for a large satellite, because the large satellite is more or less like bureaucracy. You have to ask for a target of opportunity. This target of opportunity have to go through center constraints. Then you have to reach the director. The director have to say the okay. Then you have to provide additional data. This additional data will have to go to the planner. The planner should execute the constraints if they can rotate the telescope there, and then they will rotate the telescope there. And this one can take a lot of time. On the other hand, with the smaller satellites for very bright events, and gamma ray bursts are very, very bright events, you can do that pretty much easily. And there are concepts of satellites, of putting a number of small satellites like SAASST or slightly larger, not much larger, slightly larger, in order to observe these events. And once you observe it, the relevant satellites will turn to observe it there. So with a triangulation, you can locate where exactly it is, and then you can announce the GCN for optical observatories to follow up. Because even in our case with a collimator, the signal will not be, the error cycle will be pretty large. So one X-ray source will correspond to hundreds of thousands of optical sources. Imagine that I think the PSF should be tremendous when we wish to compare it with optical astronomy. Imagine that in most optical telescopes, the field of view is 20 by 20, 10 by 10 arc minutes. And here maybe we're discussing that we might have almost 3 times that much in resolution. So the field of view will be much, much larger. So imagine that you need, in order to cover with one telescope, with a single telescope, you need to know, you have to search a mosaic of 10 or 20 exposure in optical. But if you have a constellation of satellites, then you can use a triangulation technique similar to the one that they are using in Meteor network. So you can pinpoint the location. Of course, we have to do the calculations, how many telescopes you need to pinpoint it down to 10 by 10, so that you can fit in one field of view of an optical telescope. But there are concepts like this. There are concepts of satellites to have 8 or 9 or 10 satellites to do exactly that.
Okay, thank you very much. Great.
Thank you.
Thank you, Antonios. Thank you, Professor Mashfour. Hisham is you. Dr. Hisham. Dr. Hisham is our moderator, so he may want to sleep. Okay, so he's not answering. So I believe, thank you very much for attending this seminar. So wish the best for everyone. And hopefully we'll have more chance to talk about what we are doing at SAASST in the coming seminar. Thank you very much. Thank you.
Thank you. Thank you.
Thank you.